Thanks, SK. So I'm here to talk about air traffic management, and as SK mentioned, I have a joint appointment in the Smith School of Business. My field is operations research, so if you don't know, I mean, that's actually very closely related to systems engineering. And in fact, operations research occurs both in business schools and engineering schools. In business schools, it's kind of called management science, and engineering schools, operations research. It usually happens with industrial engineering in engineering schools, and high degree is actually from engineering school. So I'm co-director of NEXTOR, the National Center of Excellence for Aviation Operations Research. So NEXTOR is a 5-university consortium: Maryland, MIT, UC Berkeley, Virginia Tech, and George Mason. Here it's housed within the ISR. We have, over the years, had faculty and students from business and both operations research. We have some people in transportation economics, civil engineering, electrical computer engineering, aeronautical engineering, applied math, and economics. Primarily funded by FAA. It's an FAA Center of Excellence. It's also been, over the years, funded by NASA, airport operators, aviation industry, and the research program is very broad, as you will see. Just to say who's currently involved, so Dave Lovell, Bob Hoffman, Martin Dresner. So David Pierce, there he is over there, he's in civil engineering. Martin is in transportation economics in the business school. Bob is a former PhD student in applied math here. He's now at a company called Metron Aviation. We have a very close relationship with that company, and it's actually a conduit to getting many of our ideas implemented. And here you see the list of students. Some of them have just recently graduated, but as you can see, they've come from many disciplines. All right, first question I'm going to just generally say is, why are these problems hard? And maybe you don't need to be convinced they're hard, but I think they have some pretty unique characteristics that make them pretty hard. So they're large. There's about, on the average, 50,000 domestic U.S. controlled flights per day. They're stochastic, got lots of uncertainty in the air transportation system due to weather, among other things. They're dynamic. You constantly have to have opportunities and the need to change decisions over time. And there's distributed decision-making and control. Now, people like John Barris in the audience will say that doesn't make them hard. Telecommunications problems have all those characteristics. Manufacturing problems, even lots of problems have those characteristics. Okay. But let me give a few things that make them really hard. So we talked about distributed decision-making, but distributed decision-making here is a little strange compared to some other systems. So you have a central kind of coordinator, which is the FAA, and even the FAA is distributed in who does their decision-making. But then you have the airlines, which make lots of decisions in this whole situation. But the airlines are competing economic entities, so they do not all have the same objective function. So you get into a lot of concepts from economics about how do you motivate them correctly and how do you get everybody on the same page in terms of driving toward a system optimal. Second point in the second box is extremely high levels of safety are required. Safety just totally pervades everything. In any system you create, you have to worry a lot about safety. And that just is sort of another added constraint that really makes things a lot more challenging. Then there's a large unionized labor force, the air traffic controllers. And in fact, these two kind of interact, because the air traffic controllers, they say, we don't want to do this because it impedes safety. Somehow you say, do they really worry about safety, or do they just not want to do it? So there's sort of, there's this issue that people can play the safety card and say, I'm not going to do that because it's unsafe. And, so there's sort of an interaction there sometimes. Government control, regulation, politics. So, sometimes Congress declares that the capacity of LaGuardia Airport is increased by 30%, but it hasn't increased by 30%. They allow 30% more planes to go there, and all think everything melt down. That happened at one time in history. So And finally, there's international harmonization. We can't just here go and decide to do X, Y, and Z because planes fly from here to Europe, and that's a whole other challenge. So, I think this box here is pretty unique, and is a whole other dimension that some other systems engineering challenge or problems do not see. Okay. So outline, I'm going to talk about delay trends, cost of delay. There's a big new effort going to change the air traffic systems in US and Europe called NextGen and Cesar. I'm just going to talk about those briefly. Then some specific projects we've been involved in. All right, so first of all, just to delay trends and cost of delay. So actually, everyone always puts up here delay trends, but we've actually been involved in research related to this. So in particular, we've done a lot of work where we will look at different performance statistics within the National Airspace System and try to answer questions that are important for policy, et cetera. Also, we recently had a project that all the NextOR schools participated in called Total Delay Impact Study, and it estimated the total economic cost of air transportation delays in 2007. And this just was not a statistics gathering exercise. As part of this, we developed a lot of new science in this particular area. So here's just a delay trend graph. This starts in 2000, but it's normalized to 2002. So the brown is delay, the green is operations. So 2000, you may or may not know, this was at that time considered was the biggest delay year on history. And then, of course, with 9/11, et cetera, the delays drop substantially because demand drops substantially. So you see the green goes down, the brown goes down. There's been a steady increase until 2007, reached the same levels as 2000. So we kind of got back to this sort of highest delay year we've seen. One interesting thing, though, as you might notice, is that the green line, say starting 2005, 2006, it doesn't increase that much, but the brown continues to increase. And one problem that the FAA posed to us was, why in the world, in fact, Congress kind of posed it to them, operations haven't gone up on a nationwide basis, but delays have continued to go up, and why is that? Well, the basic reason was that operations moved from lower density or lower congested areas such as St. Louis to areas that were already congested, such as the New York, for example, Kennedy Airport had a huge increase in traffic, whereas other airports in less congested areas had a decrease. So the operations in the U.S. stayed the same, but delays went up because the concentration of operations shifted. All right, our total, this economic cost of delay study 2007. Here are some numbers. I'm just throwing out the numbers. These are billions of them. Yeah.
I'm sorry, but in the last statement that you made, why did they shift? Was there something in terms of that?
I mean, a lot of it is just it just has to do with airline behavior and competitive positions. Delta wanted to build up service at Kennedy, for example. That's one of the reasons. All right, so this is our sort of the bottom line of the results of our study, and all I can say is there's a huge amount of sort of science underneath this, and I think a lot of things we do were sort of innovative and different from what some others did. And I'll just point out the area of passenger delay. Here's the breakdown on passenger delay costs, and so the first item, scheduled buffer. This is the fact that the scheduled time of a flight, the nominal time it takes to get from here to, say, New York might be 45 minutes, but the scheduled time might be an hour and a half. So the airlines build a huge amount of buffer into their flights for a variety of reasons, and so that's sort of the cost of that aspect. The one area where we, as a group, did a lot of research over the years is in passenger delay. So you typically equate passenger delay to flight delay. So you say the average flight is 15 minutes delayed, or the total flight delay is however many minutes. But the question is, what is the passenger delay? Well, the passenger delay is greatly increased by what are called disrupted passengers. Disrupted passengers are those passengers who start out thinking they're going on, American XYZ, but end up having to go on American ABC because the flight might be canceled when they get to the airport, or because they miss a connection. And as you can imagine, there's a lot of modeling. So look at these two lines: delay due to flight cancellations, delay due to missed connections. These are not statistics gathering exercises, well, there's a lot of statistics in them, but you have to do a lot of modeling to determine, to estimate these quantities. So there's models, there's econometric calculations, etc. Another area, and this is actually what Prem, our here did, is capacity-induced schedule delay. So this is the degree to which the sort of bumping up against the capacity constraints at an airport forces airlines to schedule in places they would rather not schedule. So the flight only exists at 7 in the morning. If the constraint wasn't there, it might exist at 9 in the morning. Now there's a lot of this sort of schedule delay for normals or just for other reasons, but this we were able to isolate the schedule delay due to the capacity.
Hey, Mike.
Yeah.
So if a passenger is delayed by, say, 2 hours, how do you estimate economic cost to that?
Well, there's a cost of, there's different cost of time for leisure passengers, there's different cost of time for business passengers, there's percentages of both types, etc. So the factors kind of depended on those two things. It was kind of a, basically different factors for business and different factors for leisure. There was actually some other sort of more subtle analysis in this, but this number, they talked about overnight stays and things like that, what's that versus other things. But these numbers basically to a multiplier based on the two things. Okay, so now NextGen and Cesar. So both the US and Europe are undertaking major initiatives to fundamentally change their air transportation system. The US is called NextGen, and Europe is called Cesar. I tried to find a nice slide that sort of illustrated this, and there actually isn't one, at least for an audience like this. So this is kind of my take on the value proposition of NextGen, some of the things that are involved with it, and this is also Cesar, and why it should substantially improve our air transportation system. So first of all, we're going toward GPS-based navigation and improved avionics on the aircraft, which means more precise trajectories and maneuvering. Now the cockpit, that is the pilot, will have total awareness around him of all the traffic around him. So what that means is that for some processes, the controller actually can be taken out of the loop for many operations, which can mean greater precision for timing and reduced reaction time. So for example, when you're approaching a runway to the airport, the pilot can very precisely, there's a certain time you need to have spacing between aircraft. The pilot now controls that and can very precisely determine the space needed behind the aircraft, rather than sort of going through a loop with the air traffic controller, which is a much sort of looser control loop, and as a result, you can increase the throughput into an airport. GPS-based navigation trajectories follow arbitrary points in space and can be dynamically adjusted. So some of the benefits: greater traffic density in non-radar areas such over the poles, oceans, Gulf of Mexico, more routes in and out of metroplexes such as New York, improved ability to land in poor weather conditions, better ability to dynamically react to changing weather conditions. So weather conditions change, you can immediately kind of reroute traffic around the weather or through the new weather. More precise timing of arrival and departure traffic streams, and as a result, increased airport capacity. Just to give you a picture of these, this is some projected routes in and out of New York. Now this might scare you a little bit, but at this point this is not really being done. But this is LaGuardia, this is Newark, and there's something called RNP, Required Navigation Performance. So with improved avionics, the aircraft they have a very sort of an error band that they can stay within. So what this shows is a departure route here, a departure route here from LaGuardia. These are two departure routes from Newark. And we sort of got this departure route kind of coming parallel, but in the opposite direction to these departure routes. That's something they don't do right now. But with the improved precision, this is something they're thinking about. So anyway, it just sort of gives you an idea. And part of it is that with the improved navigation performance, you can have these error bands and precisely stick to them. Okay. All right. So now let's talk about some major projects. We've been involved. This is a major project funded by NASA here. And what we try to do is look at stochastic problems or stochastic issues, explicitly modeling stochastic issues in air traffic management. By the way, there's no clock in this room, so I better take this out so I can watch my time. Okay, so right now, so this is sort of in some sense, the way things are done now, these two types of air traffic management procedures. But so what I'm going to illustrate is how some of our research is directed toward these ideas. So first of all, the two major air traffic flow management initiatives used in the U.S. now. One is called the ground delay program. And what happens, this is used when an airport has a low ceiling, and as a result, the arrival rate into that airport is reduced. So the classic case is San Francisco, when the San Francisco fog comes with, if they have a high ceiling or visual conditions, they have two closely spaced parallel runways. The planes can kind of come in like this. They have to kind of see each other, and they come in very close side by side. In low ceiling, that is not considered a safe maneuver, so you can only have one stream of aircraft coming in, which effectively reduces the arrival capacity of the airport in half. That's probably the most extreme case, but for all airports, there's some reduction. Airspace flow program is similar to ground delay program, but it addresses a disturbance in the airspace. So this just illustrates the reason for ground delay programs. So this is the capacity under visual flight rules. This is the capacity under instrument flight rules. This is the demand. So, the airlines typically schedule their operations more toward the green line than the red line, which means when the capacity drops to the red line, we're overscheduled. So the questions are: how do you absorb the necessary delay before the you can do it before the aircraft takes off or while airborne. If the whole ground delay program says do it before the aircraft takes off. How do you hedge against uncertainty? And then, as we'll see, there's issues of equity when we start getting into these things. All right, so this is just a picture of a ground delay program. So we have an airport that's impacted here. Sunny skies. This is Baltimore. This is Boston. Sunny sky in Baltimore, but you're sitting on the ground. Why are you sitting on the ground? Because there's a problem in Boston. We want to slow down the rate of flow into Boston because it has a reduced capacity, even though it's sunny here in Baltimore. So generally, if we think of the problem, delayed arrivals. So the problem is the control time is the flight departure. That's the control variable. But the decision variable is the flight arrival time. So you kind of determine a new flight arrival time, and then you back that up to a controlled departure time. So if you delay the arrival by a half hour, you delay the departure by a half hour. Okay. This is just an illustration of the en route problem. So you might have a string of thunderstorms or weather conditions you can't go through. And in some cases, there's a reduced capacity here, so there is some flow, but it's reduced. And then you have options of maybe waiting for a while and going on your preferred route, or taking an alternate route around the weather. Ground delay programs and airspace flow programs are almost often motivated by weather problems, and as a result, they inherently require decision-making under uncertainty, because weather is uncertain. So the whole things are, based on weather forecasts, really. The basic controls apply to ground delay programs, and some of the ground delay airspace flow programs, ground delay recruiting. So this whole project was to try to model explicitly some of the stochastic effects. So what I'd like to do is just illustrate recourse actions. That is, if you make one decision and things change along the way, how does the decision change? So for the rerouting with recourse, let's say we initially go on this route around the weather disturbance. While we're en route, the weather clears, and then we can, revert back to our preferred route. And, the point of this, though, is then to take the fact that this might happen, this can happen, into account when we do our original plan. So that's the notion of this planning under uncertainty, taking this into account when we make our original plan. Ground delay with recourse, this is now a timeline. So let's say this is maybe when we were, I guess this is somewhere in here is when, probably in here was when we were supposed to arrive. We were given a ground delay, so we're saying you're given a slot an hour later, which means you have an hour ground delay. So you're serving that ground delay. I'm sure you've experienced this. You're in the airport, and they say, we've got an hour ground delay, so you go into the bar and have a beer, and then you notice, well, the weather cleared. Now we're going to say, well, we can let you depart now, so you depart after only serving a half hour of your ground delay. Hopefully you're not in the bar, you can get on the plane. But the point of this is that originally we decided on an hour ground delay, the weather cleared, and then we were able to reduce the ground delay, etc. So this is again this recourse, and the idea is we want to take this into account when we do our original plan.
But are you allowed to do that? I mean, I think airlines, once they announce a delay, they can't roll it back, can they? Or maybe they can.
Well, certainly they do that sometimes, but no, what the airline does and what's done behind the scenes are two different things. So, for example, the FAA could say, we're assigning you an hour ground delay, but the United knows, well, if things clear up, that could be a half-hour ground delay. So they don't tell their they shouldn't tell their passengers don't go away for an hour. They should say, well, it's at least a half hour. It might be an hour. So
they actually tell you an hour usually, but they say this can change at any time, so you should be
Stay in touch.
Yeah, stay in touch.
I mean, different airlines do different things, but yeah. So the basic, I mean, this is sort of a dead simple idea, but actually there's a little more to it than meets the eye. But the way ground delay programs are done is basically you just say, I got all these flights. They all, they can't come in on time, so you just kind of spread out when they come in. So it's called ration by schedule. You just prioritize them based on their scheduled arrival time, and you stick them in the slots that are available. So this is called ration by schedule, and I won't go into a lot of the details, but it was actually a change in some things they'd done before, which was ration based on expected times of arrival. And this was sort of agreed upon with the airlines through some sort of wargaming exercises, and it has some very desirable properties from an equity perspective. Now, let me...
So this is like a fairness measure.
A what?
Like a fairness.
Fairness?
Fairness.
Fairness, yes. Fairness, right. Fairness, exactly right. Yeah, exactly. I agree. Yeah, you're right. Okay. Now, let me come up with an alternative that we have proposed. So, for each slot, in order of slot times, of all eligible flights that have not yet been assigned, choose the flight with the longest distance from the destination airport. Now, why might we do this? Now, let me tell you part of the motivation. Even under the previous technique, ration by schedule, some flights are exempted. Long-haul flights are exempted. So if you're running a ground delay program in Boston, why might you exempt a flight in San Francisco? Well, the program in Boston, let's say, is that, the flight's supposed to arrive at 4 o'clock. You have predicted bad weather at 4 o'clock. That flight in San Francisco is going to take off at what, 10 in the morning? So you're saying, I'm going to delay the flight in San Francisco at 10 in the morning because I think there might be bad weather in Boston at 4 in the afternoon. So, this sort of logic says, maybe I should kind of hedge my bet somehow. And basically what you're saying is, let's try to solve the problem with flights closer in, right? Let's try to solve it with, if the weather, if it still looks bad, we'll just delay, flights from O'Hare, or flights from Washington, or flights from Atlanta, etc. Now, we formally studied that and proposed an alternative, and it's this ration by distance. It now says give priority to the long-haul flight. So just go ahead and do this, and we're able to show that under certain models of how this works, which are very, cover most of the cases, for each possible time when the ground delay program might be canceled because the weather clears, it minimizes the delay, and as a result, it actually minimizes expected delay. So if you do this, it minimizes the expected delay of the program. Now, thanks to John mentioning fairness, the problem with this, though, is it equitable or is it fair? Well, give an example. Let's say you're running a 4-hour ground delay program. A flight A is a short-haul flight. So the classic example is a flight from Monterey to San Francisco. It's actually less than an hour. Early in the program, flight A would receive the lowest priority. So let's say it's supposed to come in at 4, the program's running to 8. It's sort of put to the back of the line, and it doesn't come in until 8. So it actually might get something like a 3 or 4 hour delay because by my priority scheme, it's sort of at the back of the line. And in fact, that's exactly why the other one is considered fair, because it sort of does it based on schedule. So how can we compromise between these two? So we have equity-based RPD, which uses the RPD priority, but places a limit on the maximum deviation between the slot each flight receives and its RBS slot. So for example, let's say its RBS slot was a 20-minute delay. If our parameter is 15 minutes, then we say no flight receives more than 15 minutes over its RBS delay. So it's like a fairness constraint. We're saying the maximum sort of unfairness of a flight can get is 15 minutes. So the way you can sort of look at this, it's like a multi-objective problem. We have illustrated here. The bottom is deviation from the RBS slot, which is a metric for fairness. This on the y-axis is total expected delay, and this is like an efficient frontier. And what this illustrates, the black points are our procedure. The other points are the existing procedure with these exemptions. And you can see we actually, this efficient frontier dominates this efficient frontier. So a lot of these points, you get both improvements in both the expected delay and the fairness of the procedure. And also another property it has is there's a lot more options to choose from. Okay, so in fact, one theme of a lot of our work is the explicit modeling, explicit metrics of equity and fairness in the system, and this notion of trading off fairness and efficiency. Okay, we now talk about the en route problem. Time here, okay. So again, this is a picture of the en route problem. And let me just now think about routing strategies. So now this box is our storm, and this is kind of the extent of it, and this is our origin and our destination. And so, you typically think, well, there's a storm there, I'm going to route around the storm, so you route around the storm. And of course, I talked about the recourse actions. Well, what if, you're halfway along the way, the storm clears, so you're a little bit into your trip and the storm clears, then you can sort of go directly to your destination. So that's sort of maybe the typical way you think about that and what our model would take into account. However, there's also an option. You say, well, I think the storm, I'm an optimistic person. I think by the time I get there, the storm might clear. So you just fly directly at the storm. And of course, if the storm clears, you don't suffer any delay whatsoever. So this is another possible strategy. And you might say, what about sort of a hedging strategy like this? You start out sort of halfway, the storm clears, etc. Well, it turns out All of these strategies are the best strategy under different conditions. The conditions depend on the geometry of this picture. They also depend, obviously, on the stochastic characteristics of the storm. So that's one area we've been able to characterize the different solutions to this problem for a single aircraft. Just a side note, by the way, in all cases, there is a contingency plan that protects against the worst case. So in all cases, this is sort of the worst case for this one. And, you sort of, if everyone does their worst case, everything sort of works. There's enough capacity, et cetera. So you sort of have a built-in contingency plan against the worst case.
Mike?
Yeah.
One might get the impression, just looking at that picture, that reorganization of trajectory is a 2D problem, but it's genuinely 3D, isn't it?
Right.
That you can change altitude and...
Yes, yes. So, I mean, in a lot of the cases, if you can fly over the storm, you fly over the storm. So most of the cases we would deal with, you can't fly over the storm. So it's sort of a 2D problem, but you're right, absolutely.
Mike, when you study these things, do you study them by simulation, or do you have a mathematical model that avoids simulation entirely? And how would you know one strategy is doing better than the other? Do you simulate 50,000 flights? And
No, we have mathematical models. Yeah. So I mean, I'll just kind of give you the single flight. There's an analytic model that characterizes the best solution, and in some of the simpler cases, you have to do a very nice sort of characterization. And the others you have to do numerics. It's not simulation, but it's a numerical solution of some model. Now the multiple flight case. So we have a large-scale integer program that optimally assigns ground delay and or reroute options to each flight, taking into account geometry, storm characteristics, as well as airspace capacity. So for each flight, their individual optimal solution might not be the system optimal solution by the time you take in all the constraints. One thing, one interesting aspect of this is that it's kind of interesting that even though that sort of hedging model, this hedging model is actually optimal under certain conditions, we have not been able to find sort of cases, we've not been able to find where it really produces a substantial benefit. So we found that the benefit it produces is very minor. So for a given flight, so what that means is a given flight, you either take the optimistic route or the pessimistic route. One of those is the best. If you just choose between one of those two, you'll sort of get 98% of the total benefit. Now, we're still, this is based on, now this is simulation. A result like that is simulation. In other words, we simulate certain kind of conditions. But, there might be conditions where that result doesn't hold up. But we're still investigating. Okay. This is maybe I'll go quickly through this, but it's kind of, we have a very extensive kind of model impact analysis, but it kind of looks at, you plan, so talk about planning versus execution. So planning, do you plan knowing about the stochastic effects and the recourse options, and do you execute having stochastic effects and recourse options? So a static reroute plan would be you reroute around the storm, a static reroute execution. If the storm clears, continue on your alternate route. So the storm clears, you don't go back to your alternate route. Reroute execution with recourse. If the storm clears, revert to the best available route. What is done today? Generally, planning is static, but execution has some degree of recourse in it. And we've done a lot of experiments which have shown the model where you plan with the recourse. Well, this just says static everything to fully dynamic. You save over 65%, which means you cut the sort of cost and delays by a factor of 3. To go from sort of what is done today to the sort of total, this modeling with recourse, you still get substantial savings, not quite this substantial. All right. Let me now talk about another project area. Yes, I'm starting to think about time. So this is an area called collaborative decision making or collaborative air traffic management that we have been involved in since the beginning of NextOR in 1996, and I personally have been very, very involved in this. So what is this all about? So it started in the mid-90s. In fact, I was kind of part of the startup of it from the beginning, although it's a lot bigger than me, that's for sure. CDM-based decision support tool and information exchange network became operational in 1998 for the planning and control of ground delay programs. Broad participation by the FAA operations personnel, nearly all air carriers, more recently business jet operators, and not just the scheduled carriers. The CDM group meets regularly to develop new computer-based tools, operational procedures. So I think this whole group is sort of unique in government-industry interaction. So you have airlines, operational personnel, and FAA people, and they meet regularly, they work together to solve problems, and everyone sort of has loyalty to this CDM group, and they're really kind of a can-do kind of group that has been very effective at problem solving and has gotten a lot of things done. Lately, it's become a little more bureaucratic, but when it began, it was really a unique kind of cool group. So some of the philosophical components: improved information, common situational awareness, distributed control and decision-making, strong interaction between airspace system managers and users. Some of the more interesting things from my perspective: new fare allocation principles, new slot exchange mechanisms, shared decision support tools, shared communication networks. All right, back to ground delay programs. Let me just mention one thing I left out of the previous discussion is there's a bigger process around that ration by schedule I mentioned. So after you do that initial rationing, airlines go through a flight slot assignment, reassignment. So when airlines tell you this flight is delayed an hour, and it's an FAA delay, they're slightly lying, because what happens is the FAA assigns all the flights to sort of delays and slots. So let's say United has 100 flights coming into O'Hare. They assign them all arrival times. Well, what the FAA assigns them arrival time. What United can do is say, I got those 100 arrival times. They're like slots for my flights, and they can totally shuffle the flight to slot assignment. Another thing they do is that they strategically will cancel flights, and you cancel an early flight, and you can kind of do a daisy chain of moving flights up into those slots, and by canceling one flight, you can reduce the delay on a lot of other flights. So they have a huge amount of control over exactly what happens. So this is sort of an intra-airline slot exchange. This is actually kind of an inter-airline slot exchange. Occasionally there's a slot an airline can't use, so maybe United gets an early slot, the flight that's supposed to go into it, the equipment got in late or had a mechanical problem, it can't use it. There's a way of trading slots between airlines to get United a slot they can use and trade that to some other airline. So one thing that this is just a list of recent research we've had in this area. So what I'm going to talk about is slot exchange models, explicit modeling of uncertainty, whole issue of equity and fairness, again, new allocation equity standards, allowing airlines to input preferences into resource allocation mechanism, integration of surface data into TFM decision making. All right, just this issue of slot exchange, I want to talk about it. So as I said, the intra-airline slot exchange I mentioned, and then there's this inter-airline slot exchange, which is this compression. One thing that we have done is looked at slot exchange alternatives. So just thinking very broadly, compression is a batch procedure. You can think about making it a transaction-oriented procedure. And in fact, that has been done. And we have done a lot of analysis related to making this a transaction-oriented procedure. Another extension is right now, it's like a one-for-one trade. You can kind of go to K to N trades, and I'll illustrate that. These are kind of futuristic things of actually making it a real market with payments. That is resisted a lot and certainly has not been done. But just to illustrate this one-for-one trade to two-for-two trade, or K for N trade. So compression is a one-for-one trading system. Airline gives up a slot it can't use for one it can use. You might say, well, what about a more general trading system? So let's say United has these two slots and American has these two. Let's say this flight is really important to United, this is less important. It would be willing to trade to American so it could reduce the delay on this flight and pay for it with increased delay on this flight. Similarly, an American might say, well, this is my important flight, this is less important, so this trade might make sense to it. It also might want to move these flights closer together for banks or whatever. So this is a trade that can make both better off in certain conditions. So we've done simulations of this, and this is sort of, we simulated an airline objective function. This is sort of the system-wide optimal. This is for a whole lot of ground delay programs. This is percent improvement over the max possible. So this is 40%. So the max is close to 30 and 40. This is what you can do with the current procedures. As you can see, with this new trading mechanism, you can almost achieve this system-wide optimal. And this, by the way, is a typical way distributed mechanisms are evaluated in economics. You say, what is the system-wide optimal? And then you have to have a mechanism, a market mechanism, or a trading mechanism. And you say, how close can I get to the system-wide optimal? As you can see, we got pretty close. Okay. Just some comments with some other kind of, so to do this, we simulated an airline cost function. Because the total delay on all the flights stays the same, but this allows the airlines to better sort of optimize internally. Okay, maybe I should think about wrapping up, and I'll just, why don't I try to wrap up? And I'll just mention this last project very briefly. The last project, we actually did work for the FAA policy office. So about 4 or 5 years ago, there was a, so maybe I'll say one thing here. You might know about slot control. So slot control says, there's a limit on the amount an airline can schedule at an airport. Well, virtually every airport in Europe is slot control. So, Lufthansa can't just go and, say, I want to offer 5 more flights into Frankfurt at between 3 and 3:30. They have to have a slot to do it. In the U.S., there's just a very few number of airport slot control. And, so it's sort of interesting why there are all the differences. But anyways, the slot control legislation was expiring for LaGuardia. And we worked with the FAA policy office to kind of explore other options. And I don't know. I want to say one thing about the project here. This was sort of a cool project in that we conducted 2 multi-day strategic simulations. So they're like wargaming exercises that brought together decision makers from airports, airlines, and the federal government. So we had a mock. One thing we did as part of this was we actually proposed auctioning off landing slots. And we had a mock auction. We did some other things where we brought all the airline people and others together. And so it was very kind of interesting kind of wargaming exercises that we did as part of that. But sort of to get to the bottom line, we did a lot of research related to this, and it was actually used as part of justification for some FAA rulemaking. And one of the things in this rulemaking was that the FAA would conduct a slot auction, so they'd actually auction off these landing slots. This would have been the first time in the history of the world that that was done. And I might say part of the team was 2 of our economists from our economics department, Peter Crampton and Larry Alsabel, who actually are 2 of the world's leading experts on auctions. They're here in Maryland. Anyways, they were part of the team. We got up to sort of a month before the auction was going to be conducted, and the airlines and the Port Authority of New York and New Jersey stopped the whole thing in court. This was just at the end of the Bush administration, and when the Obama administration came into power, the Democrats were sort of very much entrenched with some of the political interests of the airlines and the Port Authority, and the whole thing was dropped. So we never had an auction. But anyway, it was quite an interesting exercise. All right, so let me close here. So final thoughts. I think this represents a challenging research area of international importance. We brought together a lot of disciplines: systems engineering, operations research, transportation, aeronautical, economics, applied math. And I just should say one thing with this NextGen, there could be some very major, substantial opportunities, funding opportunities in this area. And you know, I think we have some sort of conduits to some of that money. So I mean, you know, might be talking to others about some opportunities in the coming months. So thank you. Questions? Yes.
So in seeing some of the slides where you illustrated these trades going on between, say, airline A and airline B and slots 1, 2, 3, etc., with better slots, worse slots, it occurred to me that perhaps there are partner airlines. So instead of just airline A and airline B, there is partner group of airlines A and partner groups of airline B, and maybe C, D, and E, etc., such partners.
Right.
So then among these partners, there could be internal intra-partner exchange,
Right.
but that may only happen if there is matching conditions satisfied. So if there are mismatches, then you now have to go outside your partnership. And so this idea brought to mind things like organ exchanges and stuff that involve multi-way
Right.
exchanges that you know about, I'm sure.
Yeah.
So is there any merit, because you believe that among partners there is some
Yeah.
sort of altruistic
Yeah.
behavior,
Yeah.
again, so
Well,
you know what the story is.
A couple of comments. First of all, the major carriers typically control the slots of their sort of commuter partners. You know, like United would control the slots of United Express or things like that. Now, in terms of doing that in an alliance, it's not done in alliances. Now, one thing is typically the international flights are not involved, so a lot of the alliances are
International.
I think there are some antitrust kind of issues. So you're starting to get into a gray area in terms of those kinds of issues. You know, if a given airline can say, I'm only going to trade with these airlines, because in fact, there's sort of some fine lines in this whole CDM stuff about antitrust issues, and there's some special antitrust immunity they're given, but there's a lot of sort of touchy areas there. And I think if a given airline can say, I'm only going to trade with these, I think that's probably not going to fly. Although they do it for their commuter partners. That's certainly true. Yeah, John.
You have weather prediction for that, but that case it's only 70, so we are talking about the 70 by the 70. And they are trying to use some online from other aircraft or from whatever. So where does it into consideration? And the related question is, when you describe this study given a uncertainty model, what sort of vastness is with respect to uncertainty about the 70?
So the first part is sort of how does weather prediction fit in? I mean, the truth is there's not a lot of sort of good, well, just the weather data is usually, they don't give it to you in a form that helps you. You know, you kind of want stochastic distributions. Now there are some exceptions. There's a nice system in San Francisco that actually produces kind of a distribution of when the weather will clear. And we've actually worked with them, and even that, though, they don't quite use the power of it. But that is one exception. You know, for some of the work I showed here, you know, we kind of pose different distributions. And the truth is there is a little bit of a disconnect between, you know, getting the right data out of the
But I
weather
think what we do
information.
was, I've been in flights where the pilot says you have to receive information from jets and aircraft.
Right.
Right, they change.
Yeah, right.
How expensive is this?
It's not formally integrated into the whole, but I think that's certainly
That's an
a
area.
promising, absolutely, yeah, that's a promising area, absolutely. You know, sort of the plane as a sensor, basically.
So 8 times that with respect to in our right-hand corner, we try to talk about solutions if something changes.
Right.
We've done studies like that here, where the stochastic model changes a little bit, especially because you don't know it precisely.
Yeah.
You try to say, well, you know. I'm
Yeah, I
good
mean,
for
we've done a
this.
little bit of that, but not, you know, I mean, one thing we've been trying to do more recently is, the big thing from getting something implemented is to make sure you protect against the worst case. So we're starting to think in those terms a little bit, to make sure if everything goes to hell, you sort of have a, I mean, that's the thing that really prevents things from being implemented. If you know, the controllers and the air traffic specialists feel, you know, they feel uncertainty about what happens in a worst case situation. That's sort of the key thing you have to protect against.
Because usually statistics, you're given some model, but then you're given confidence again.
Yeah, right, yeah.
Model.
Let others have a turn and I'll come back to you.
Have you also looked into the extreme but the rare extreme but important cases like the volcano in Europe or
Oh.
like that?
Didn't look into that, although I was at the FAA during that time, and the guy that was telling me, you know, we could start a whole research program on this because there were so many. You could say you could even get UAVs, you could have UAVs fly through the bad weather to see if, you know, fly through the volcanic ash to see if that was okay. You know, so, but yeah, I don't. One area that has been research on is space, you know, interaction between, you know, like the shuttle, and in fact, we've done some research, not we, but some of the other schools. But some extreme weather events, we haven't really done anything. Yeah.
What do you envision the role of the pilot being in essentially automated?
Well, certainly, I mean, the pilot will have full situational awareness and really have some of the responsibility the air traffic controller has right now. That whole area is very sort of touchy. And again, that's where the union sort of becomes involved. So a lot of people will privately tell you, you know, there won't be air traffic controllers, but you know, you can't say that out loud. And at least people will say the role of the air traffic controllers will change. But the truth is, the pilot will have more responsibility. Although the truth is, the cockpit, a lot of this will become automated. In other words, it's sort of even today, there's a lot of systems now where you know you automatically detect collision avoidance system, you detect the collision, etc. So
But then it becomes an override become really,
yeah.
you know, what
Right.
you know, how do you build in the error?
No, absolutely, and in fact, you know, everyone says the model where the controllers step in when there's a problem, that's just not a good model. Because, you know, they need situational awareness, and they can't just jump in when there's a problem and you expect them to save the day. I mean, that people trying to say that's not going to work, so. Yeah.
Yeah, so you're talking about using GPS to achieve closer, you know, more precise navigation and have aircraft be closer. I mean, as a technology, is there willingness to rely on GPS? Is it reliable? And I mean, in the rare, I'm presuming it is, and in the case that it for some reason fails, which I'm presuming is rare, is there a fallback? I mean, the pilots are very close by, suddenly GPS fails, now what? Is that something that?
Well, first of all, you know, there are systems they have put in place, they're putting in place to make it more accurate. So it has to, the standard GPS that you have in your car is not accurate enough. So you need higher accuracy. In terms of, you know, but the whole issue of backup is a big issue. So, I mean, but certainly that's a problem that's being worked, and, you know, there's sort of fundamental backups they're putting into this GPS system. But yeah, I mean, that's the whole issue of failure modes and everything else. That's certainly a big issue with all this. Obviously, for good reason.
Many uncertainties exist in the system. Does this model always guarantee an optimal solution?
Well, any optimal solution is optimality is a mathematical idea. So within this given model, gives you an optimal solution. but every model obviously, leaves, you're always, particularly when you're talking about modeling uncertainty, there's pieces you leave out. So
You have many metrics.
yeah, you also have multiple metrics. Yeah.
Some kind of issues of like, for example, pilot variability or pilot compliance and kind of individual performance metrics. I don't know if those are tracked. I don't know if those would feed into this kind of NextGen model if the pilot suddenly requires a lot of new power. That's the first question. The second question is, where are your frequent flyer miles? You fly
Well, the first thing I should say is there's a lot of human factors research in this area. We don't do it. Actually, they do it at MIT. They do a lot of human factors. So there's a lot of people who do human factors research in this area. It's actually been a little more focused on controllers, but for the reasons you mentioned, you need it for pilots as well.
There was
So-
some studies in the automotive right? The path and other stuff.
Right.
Where they actually ask this question, how powerful is the driver versus the rest of the people versus the control might.
Right.
So who do you fly with?
Well, I have more United miles than any other, but that's another Yes, Kate.
So, once UAVs start getting into the picture and applying commercial airspace, will higher notion of what this means, safety,
Right.
going to be operating with the entire sequence of the rules.
Right.
So what happened in that case? There were two players, and one is
Yeah.
rather worried about safety, and one people are, kind of saying whether this aircraft cost us for $500 and we're not going to do it.
I mean, the first answer is that UAVs is a big part of NextGen and CISAR. That's integrating them in is a big thing. Now, whether that's solved yet is another question. I think a lot of the UAV application is supposed to, it would be in sort of dedicated, like low altitude airspace and things like that. But when you start having UAV traffic integrated with others, actually, a lot of people will say, they're much more confident flying a plane without a driver than a car without a driver. Yeah.
You spent a lot of time talking about minimizing delay. Have you considered incorporating the cost of doing that into your decision?
Cost of minimizing the delay or the
cost of some other issues like the fuel and you cancel it sometimes you have to
right. Yeah. So one answer, which is a little bit of a cop-out, is to say a lot of this sort of collaborative decision-making stuff tries to give the airlines control over things. So, for example, you give the airlines lots of flexibility. If the airline can then decide whether it wants to cancel more flights or less flights, whether it wants to minimize fuel or minimize this, etc. So there's sort of a philosophical component that some of those trade-offs like that are up to the airlines, and you want to give the airlines as much flexibility as possible to sort of optimize. Each one has their own objective function. To a certain extent, the airline, the FAA objective function tends to be oriented toward minimizing flight delay and equity. And to a certain extent, this is sort of it's actually kind of a nice, they don't care whether it's a big flight or a little flight, but then they just give the airlines the flexibility. And then the idea is to let the airlines optimize those things. That's kind of the philosophy, but certainly things like environmental and fuel are becoming more and more important, so I think it's sort of drifting into even the FAA side.
To expand on Mike's point a little bit, the relationship between things like fuel burn and emissions are fairly linear in delay length. So it's sort of, if you're working on one, you're not directly, but it's a pretty strong correlation to working on those other kind of things. functions of the way like.
Yeah.
Is there any significance to the fact that in the results that you showed, the amount of cost due to delay was equal to the total of the cost between, it was cancellations and, I'm sorry, and missed flights? I mean, was that just
No, that's, no, there was not, no, I mean, that's sort of by chance, I guess. But one interesting thing is that it is equal, which means it's actually, if you look at flight delay, a rule of thumb says double that and you get passenger delay. Because that's kind of an implication of that, what you just observed. So if you say total flight delay was 1 million hours, total passenger delay is 2 million hours because of these other effects. That's kind of a rule of thumb. All right?
Again, to the next question. In the problem where you were trying to do the collaborative decision making and allocating slots, right? You can use option mechanisms.
No.
So
There's no money involved.
no. As a method, how do you guarantee the integrity of the lease? So is weekly auctions something that should play a role here or not?
Well, certainly when we looked at the slot, the last thing I talked about, that had big,
Trying to avoid the problem where I'm bidding here because I'm waiting to go there because I'm not taking advantage to go there. You know, the class problem in all this allocation.
I mean, the last application, which is the combinatorial auction for the long-term slot leases, that certainly, the notions of a victory auction in the combinatorial setting are very, very important and were important in what we did. And, give credit to our economists, but in the collaborative decision-making setting, it doesn't, that exact sort of context hasn't really come up.
And the collaborative decision making, I'm surprised with the point. Typically, in single collaboration, single or collaborative decision making, whatever name you want to use, we use this metric that's called the price one, right? So we compare the social, the optimal, global social optimal.
Well, yeah, right.
So is there something particular about the structure here which makes it so small?
Well,
The structure of the problem?
I mean, one thing
Because we get similar problems in communication, but under very special conditions, we get the price of energy go so low.
Would you please repeat the question?
Okay. So in the curve that we saw in the end, where you saw in that by this distributed mechanism, they were getting very close to the social optimal, right? Usually the ratio of the social optimal versus the distributed solution is called the price of energy. The energy being distributed is in the making, right? In many problems, this is 1, 1.5, 2, and so on and so forth. Here, it's, I mean, the falling.
Well, so.
Better question, what is the structure of the falling?
So this is social optimal, and this is, so the price of our mechanism almost achieves social optimal. That's what John's saying. Is there a special structure?
Yeah.
I mean, I don't know. We analyzed the mathematical structure that led to this. I kind of glossed over this point. This simulated cost function was assuming airlines optimize on-time performance. Notice this note. Performance is not nearly as good if one simulates airline objective function using passenger delay. And one reason for that is you can have the airlines that have small flights, they can sort of protect their turf, and they have no motivation to change. If you want to minimize passenger delay, you have to get the airlines with small flights to trade with the airlines with big flights, and to do that you need money. So basically the airline says, I'll trade, I got a 10 passenger flight, I'll trade it to United, I'll put an extra hour of delay on that, United gives me $10,000, right? Now you can argue whether that makes sense, whether that's a good idea or not, but it would lead to this optimal in terms of passenger delay. Even though anybody on a small flight would do.
So this results as simulations because
there's a particular cost function.
theory behind telling that because of these reasons we expect.
I don't know the theory. No, this just happened with a particular cost function. There are other cost functions that didn't happen.
They
before.
were. Right, thanks. All right.
probably should. I don't know.